So that's one small code repository where you have the root directory, and the leaves are code files, so files containing source code, and their size is according to the size on the disk. So not really how much code is in there, but just the size on the disk. So next thing to do is then embed code features into this fancy map, and the obvious thing to do is choose term occurrences. So I selected for you to play with. Oh wait, give me long. HITBSecCodec code, and it's interesting to see it light up if you search for suspicious terms. Like I tried searching for string copy. So HITBSecCodec is obviously a bit larger, 1,000 files, and you can see that there are not incredibly many occurrences of string copy in this code, but there are some. The red ones, the red ones contain string copy, calls to string copy. Which is not such a good thing for such an exposed library. And another fun thing to look for is always tag. So what do we all do if we have to implement some part in code and are too lazy to think about how to do it properly at the moment? We just write a comment and put something in there like hack. This is also not so entertaining. I mean, I haven't looked into many of them to see what the heck was at that particular piece of code, but it's just to illustrate that you have one picture and can get a sense of, oh, there's possibly some problems there. I should look into this file and down there possibly to see whether there's actually some problem. And a request for search terms.
It's me.
Yeah, that's Eclipse. It's slow, still. I don't really know which version I have. I believe it's a version I leaked 3 months ago, so pretty recent. So if any of you is bored tonight, you can have a look at HITBSecCodec. So that's one of the examples where pretty pictures can help you find your way around the source code and see what you're going to look at. That's just in case the demo wouldn't work. I don't trust computers. So that's that, highlighting search terms in source code. Another thing you can do is chart path in these maps, which can be really useful in code and data flow graphs or call graphs. So track a certain property across the code. And it's useful in any kind of tracing, be it the access to certain variables or the access to user input, or also a long-term period log acquisition and release. it's bad style to do the locking not in the place where you're actually accessing the shared variables, but somewhere else. But you see it a lot of time, and it's not always back because sometimes some of the calling, all of the calling functions acquire the lock and release it properly, but sometimes they don't. So that's one point where the code quality is bad, although there are no real bugs in there. If you change anything, you're likely to introduce strange bugs. Implementation notes on what you saw that one thing at least runs, and the work I'm currently doing is based on Eclipse and Y files. If somebody has seen Helva's work and is finding it at least visually similar to what I'm doing, that's because we use the same graph library. And it's implemented as Eclipse plugins and uses the IDE and the Java development tools and the C development tools, which are actually quite cool, although Java is a bit annoying. So why I use Eclipse is that the plugin architecture is very convenient, and it already has a lot of the stuff that I'm going to build on. I tried using OpenGrok first, but they hard-coded HTML output into the Lexer, so I'm not going to use that. So control flow graphs. We all know control flow graphs, possibly because of Halber. They have been widely used for 2 or 3 decades in computer science and compiler design and implementation, and in debugging and reverse engineering. And compiler design and reverse engineering use control flow graphs on machine level language instructions, so IL32 or whatever architecture you pick, be they virtual or real. So what actually makes control flow graphs useful in reverse engineering? They're pretty much taken for granted where I come from, but what actually makes them useful is that there's information implicitly contained in the instruction sequences. So you have just lots and lots of listings, and this information is made explicit if you build basic block graphs and depict the control flow within these graphs. It's presented in a way that's really easy to handle by the human visual system, because humans are rather good at seeing relationships that are depicted by connections between entities, and thus it helps to reduce the cognitive load. So you have to use all the cognitive resources you can get in reverse engineering because it's such a low level of abstraction. So any help in doing that is appreciated. How control flow graphs do that is by visually displaying code as lines that connect dots. So the dots are pieces of code and the lines are the flow of the possible flows of the control. And there's even research on that. So the scientists on my site, Colin Wares and Excellent Treat information visualization, if you want to know more about that. It's really the easiest way for humans to recognize relationships. Of course, there are opportunities to get even more of the human visual system, which is millions of years old, so we should use it. Animation. We already have the word flow in control flow graphs, so make just some sort of blue stuff flow along the lines. I've actually seen that. I'm not sure where. I'm not sure whether Vietnam does that. And then you get again a spatial method for sequences of instructions. So they are arranged in space and in a way that puts related code pods closer together. So once again have a sense of orientation within the code. So in theory, the cognitive effect should be similar in source code reading. There's no reason why that should be limited to machine level language code. But on the other hand, you have a higher abstraction level in source code. So if you have the source code, you want to use it. And there's another reason source flow graphs are much cooler if you have them because they're less complex than basic machine level language flow graphs, which is in here. The red region is source code basic block graphs, and the green stuff is the corresponding machine level language flow graphs. Nice to look at. So the logical step is to try and provide control flow graphs that incorporate the available source code. Something that I've first tried a year ago, and did the really entertaining thing of thinking I could just do it in Perl in an afternoon, which meant I ended up trying to write an ad hoc parser for C. I saw stars at the end of the night and didn't get much farther, so I decided to just let other people do the parsing. And this is what a hello world might look like then. So that's actually generated from code. Yeah, speaks for itself. Not much to elaborate here. Where's my pointer? Anyway. So building source code flow graphs is not really rocket science, but it's not straightforward either. The general method is that you have to get a mapping of the source code blocks, IP lines, to the machine level language that it translates to, and then construct the low level basic blocks. So you do all the things you do in machine level language basic block graph construction, plus then you take the machine level language basic block graph and the mapping of source code blocks to machine level language code blocks, and project the basic blocks onto source code using that mapping. As a result, you have the source code flow graph and the mapping from low level flow graph to the source flow graph, which is not really useful, but I like to maintain it for definitive purposes. Where did my pretty picture go? Anyway. There was supposed to be a pretty picture there. I'm confused. The mapping of source code blocks to low-level language code blocks was what I initially tried to do ad hoc. Bad idea. So option 1, build a compiler. That's what I tried to do. Not so good. Option 2, use existing tools, compilers or debuggers. And one option is using the Visual Studio compilers. With or without managed code extensions, but it's especially easy if you use the managed code extensions because there's a compiler switch that outputs .cod files, which is exactly what we need. It's just a line of source code and then the statements it translates to before optimization. So everything you do, you get before optimization, otherwise it's going to become difficult or impossible to construct the mapping between machine level language and source code statements. Other compilers and configurations are also possible, but I haven't looked into that yet. And here, the theory, all the information you need should also be in the assemblies or the PDB files, but yeah, another time. If somebody feels like coding, no, probably not. What you could also use is GCC. The data should also be available in the debugging information if you compile the code with the -G switch. And the quick and dirty pragmatic approach I tried at first failed because I tried using GDB and